Okay, so some optimization problems. So steps in optimization. Number one, identify what you want to optimize. So what you want to maximize or minimize. It could be something like the area, the volume, or a cost. After you've identified what you want to optimize, we need to construct a function that describes what we need to optimize. The function typically, when you first construct it, will have more than one variable. So once we have the function that describes the element that we want to optimize, we need to condense down the number of variables we see. So, which brings us to step 3, construct a relationship which links the variables together. Typically, this relationship comes from some limiting factor, like you have so much fence, or you can only have so much volume, or it might not be from a limiting factor, but it might be from comparing the variables, which would be something like the top is 3 times the top costs 3 times more than the bottom to make, or something to that effect. So the relationship between the variables allows us to redescribe the equation that we constructed. So use your newly constructed relationship between variables from step 3 in order to rewrite the function from step 2 in terms of only one variable. And then once we have that function in terms of only one variable, we can then differentiate. So step 5, we need to differentiate the function obtained from step 4 with respect to the only variable listed. Be sure to use the power rule to do so. If you do it with the difference quotient, you're kicking water uphill. It's going to be a battle you don't want to fight. So when I say the power rule, that's the if f of x is x to the n, then f prime of x is n times x raised to the n minus 1. So that's the power rule. So once we differentiate, simply take that derivative and set it equal to 0, and then solve for the values of the variable, typically x, which make that true. So this is precisely where the optimization takes place. When you find the values of x that make the derivative equal to 0, you're solving for the critical points, and those critical points will allow us to solve the optimization problem. So step 7, use the values of the variable found in step 6 in conjunction with the relationship from step 3 in order to solve for all remaining variables. Once you have all remaining variables solved for, it's a matter of answering the question. So that's a nice little outline. You'll see these steps also posted in Brightspace along with these videos. So let's jump into some homework problems. All right, so problem 1, solve the optimization problem. We want to maximize P where x plus y is equal to 16. So these first examples are pretty cut and dry. It's told we want to maximize P. So P is x times y, and we have the relationship linking our variables together as x plus y is equal to 16. So we want to maximize P, so P is what we will be taking the derivative of, and I'm going to use this relationship x plus y is 16 to redescribe P. So from this relationship I see that really I'd like to have P only in terms of x, so I want to replace y as something in terms of x. Well, that something comes from this equation that says y is 16, subtract off x. Now we'll shove this back into the function we're trying to minimize, or maximize. Are we maximizing? Yeah, maximizing. So P is, well, x, which is now called 16, or I'm sorry, blah. P is x times y, which is 16 minus x. And then so this is what we're going to take the derivative of. So because P is being described in terms of x, I'm just so we have the familiar notation, I'm going to call this P of x equals x times 16 minus x squared. So all I did here was distribute the x. So we have this nice quadratic equation, which I will write in standard form. All right, so there's our function P of x, and we need to differentiate P. So let's find P prime of x. Well, P prime of x, we'll take this 2, bring it down in front to get minus 2x, subtract 1 off the exponent to get a 1. Doing the same for the plus 16, there is a 1 in this exponent position, bringing it down front to get the plus 16, and this becomes x to the 0, which is equal to 1. So P prime of x is equal to minus 2x plus 16, and this is what we want to set equal to 0. So taking the derivative, setting it equal to 0, and then solving for the value of x, that makes that statement true. You might see it already. So we see that x is 8. So we will utilize this value of x being 8 to solve for the corresponding value of y. So if x is 8, well, this says that y is 16 minus 8, 8. So maximizing P is 8 times 8. Maximizing P, simply shoving in the value of x that we solved for and the corresponding y value to get the 8 times 8, which is 64. All right, so that is a little introduction. Let's see if I don't think I'm, let's try to punch this in. I don't know if I'm on the interweb or not. And in fact, okay, this is just a preview tool. Can I submit? Can submit the whole thing, but not just one. Okay, so we see that P is 64. Recognize if this said minimize P, we would essentially go through the same process. And that's because whether or not we're maximizing or minimizing, realize that essentially when we're maximizing or minimizing, we're solving for critical points. And you really don't know if those critical points are a local minimum or a local maximum. So consequently, when you do the work, do the algebra, it feels the same, because whether or not you're at a maximum or a minimum, those values are obtained from setting the derivative equal to 0 and then solving. Okay, so that's the first video on maximization. I'll see you on the next one.